Hey guys, Mr. Anziano back again with page 4 of the Unit 6 test review. So this will be part 4 of the video series. We're starting here with number 18. It says write the expression equivalent to 1/2 log of x plus 2 log of y minus log of z using the fewest possible number of terms. Okay, so first we need to realize that 1/2 times log of x can be rewritten as log of x to the 1/2 power using what I call the power property. Allows us to move the coefficient into the exponent and vice versa, right? And also 2 log y can be written as plus log of y squared. And then we have minus log of z, which has no need to be rewritten. Right, so I'm going to take this one at a time and do log of x to the 1/2 plus log of y squared first and kind of condense those two separate logarithms into one by writing it like this. Log of x to the 1/2 times y squared. Because we're adding the two separate logarithms together, we use what I call the product property to rewrite those as a single log, using a product instead of a sum, right? And then we still have this minus log of z over here, so I'm going to bring this over here. And now we're going to use the quotient power to handle that, or I'm sorry, the quotient property to handle that minus sign and rewrite log of, we're actually going to have one big one here. So the argument of the first logarithm, x to the 1/2 times y squared, I'm going to rewrite that x to the 1/2 again back as square root x because that just looks a little cleaner. And we also have y squared. So that's the product of square root of x times y squared. And that's all over z. Okay. So you can write it as log of square root x times y squared all over z. Or if you were to have moved any of that stuff around and written it instead as y squared times the square root of x over z like this. That would also be fine. Either or. Okay. And that's the answer for number 18. That's using simply one logarithm instead of 3 different ones, right? Number 19 says between what two integers does the value of log base 4 of 53 lie? Well, we did a few of these back in 6.1 or 2. We need to figure out what power to raise 4 to get to 53, right? And I know that if I raise 4 to the power of 2, I'm going to get 16. And if I raise 4 to the power of 3, I'm going to get 64, right? So 53 is closer to 64 than it is to 16. So I know that the values are going to be 2 and 3, right? The answer is simply between 2 and 3. But we also know that it's going to be a little bit closer to 3 because, again, 53 is closer to 64. So between 2 and 3. Number 20 says find the equation of the inverse function and then state the domain of the inverse function. Okay, these I think are really fun because really it's just following a few simple steps where first we begin by rewriting the function. Instead of f of x equals, we're going to write that as y equals 2 to the x minus 2 plus 3. All right, and then we just switch the x and the y variable. We switch the y there with the x there, right? And we end up with x equals 2 to the y minus 2 plus 3. And now we need to solve for y, right? So subtract 3 from both sides. And we're left with then x minus 3 equals 2 to the y minus 2. To undo the exponent, or to get that exponent to now be in the main line of work, we need to take the log base 2 of both sides to get rid of that 2, right? So I'm going to take the log base 2 of x minus 3, and I'm also going to take the log base 2 of 2 to the y minus 2, right? And log base 2 of 2 to the y minus 2, remember we can take that exponent and now move it to the front of the logarithm, and what you would have left then is log base 2 of 2, which goes to 1. So really, bringing that over here, we get log base 2 of x minus 3 on the left is equal to y minus 2, and that's it, right? Now we almost have y by itself. I'm also going to rewrite this with y on the left because that looks a little nicer, and I'm going to add 2 to both sides. So we get y equals log base 2 of x minus 3 plus 2. Or in other words, f inverse of x is equal to log base 2 of x minus 3 plus 2. And there is my inverse function. Part 2 of this question says to state the domain of the inverse, right? And the domain, to find that, well, we just take the argument, x minus 3, and set it equal to 0. And we get x is equal to 3, right? And because there's no negative in front of the variable, that means that if we were to graph this, we're going to end up with a vertical asymptote that is over here at 1, 2, 3. And the values are going to go to the right, something like that. Okay, so we know that the domain is going to be from 3 to infinity. That's my domain right there. Okay, or x is greater than 3. Any x value greater than 3 will satisfy the inverse of f. All right. So next we've got 21. It says solve for x. We get 3 minus e to the 2x plus 3 is equal to 1. Are there 0, 1, or 2 solutions? Let's find out. First, I'm going to subtract 3 from both sides because that seems like a pretty good place to start. And we will get negative e to the 2x plus 3 is equal to 1 minus 3 is negative 2. But I don't really like the negative situation, so I'm just going to divide everything by negative 1. Right? Sound good? Okay. We get e to the 2x plus 3 is equal to 2. But to undo the e, we're going to take the natural log of both sides. Because remember, natural log is just log base e, right? Just like over here we had log base 2, we did the same thing there. Well, log base e is written as natural log, but it's the same idea. Now we end up with 2x plus 3 on the left is equal to the natural log of 2. Okay, to get x by itself, we need to subtract 3, and we get 2x is equal to the natural log of 2 minus 3. So dividing both sides by 2, we get that x is equal to the natural log of 2 minus 3 all over 2. And there we have it. That's the answer for x. X is equal to the natural log of 2 minus 3 all over 2. And is that 0, 1, or 2 solutions? Well, let's actually, I'm going to pause real quick and pull Desmos up. And voila, there it is. So the question was, looking back at our work that we have here, is the natural log of 2 minus 3 all over 2 going to be 0, 1, or 2 solutions? If you haven't figured it out by now, something that looks like the natural log of 2 minus 3 all over 2, really, that's just one value, guys. If we were to punch that into Desmos, it's going to give us a decimal answer, right? So let's just see what that looks like. Natural log of 2 minus 3 all over 2. Natural log of 2 minus 3, and actually, you know what, let's put that in parentheses. Natural log of 2 minus 3 all over 2 is equal to negative 1.153. Okay, negative 1.153, which is one solution. Right, one solution. Whoop, hello. That's kind of a circle. You get the idea. One solution. Next we have, what are the values of the following? Well, the natural log of 1 is saying, what do we raise e to the power of to get 1? And the answer is always going to be 0. What's the natural log of e? Well, what do we raise e to the power of to get e back? 1. What do we raise 10 to the power of to get 10 back? 1. The natural log of 0, hey, that's undefined. You can't take the natural log of 0 because we can't raise e to any power and get 0 as a result. What is the log of 1? Well, log base 10, remember, if there's no base, the invisible base is the number 10. It's called the common logarithm, right? 10 to the power of what gets us 1? That's 0. Log of anything is going to be 1, guys. Log base anything of 1 will always be 0. What is the log of 0? Again, log of anything. Technically, this is 10, but log of anything, log base anything of 0 will have to be undefined because you cannot take any base, raise it to a power, and get 0 or anything negative as a result, right? What's e to the 0? That's 1. And we just said you can't take e, raise it to a power, and get a negative number, so the natural log of negative 1, also undefined. All right, that should be a breeze. We should be able to go through those pretty quickly. Okay, I'm actually going to pause as we flip over to the next page and get ready. Okay, here we are on page 5. Now, I took that time while I was paused to get a calculator. I suggest that you do the same. So if you need to pause to grab a calculator, do that now. Or pull up Desmos. Okay, so here we go. I've got some things on the calculator there. I'm going to clear them. And let's see what we need to do here. For page number 5, I'm going to try and get through this very quickly. So read the problem to yourself. Turns out we got some seeds. They're being planted, and we have the height of a plant as it's growing as days go by. And here's the function that models the height. And so what's the situation? We need to find h of 3.5 and h of 7 and explain what those values represent. Okay, well, h of 3.5 is just going to be, well, look at the function. That's 2 plus 50 times the natural log of t is going to be replaced with 3.5. And what does that turn out to be in your calculator? Well, 2 plus 50 times the natural log of 3.5 minus 3 is just 0.5, right? We get negative 32.66. Or let's be more precise and put a 657. Sound good? Negative 32.657. What does that mean? The shrub is still roughly 32 millimeters below the surface, right? The shrub is still about 32 millimeters below ground. Okay, that's what that means. What about h of 7? h of 7 is equal to 2 plus 50 natural log, 7 minus 3 this time. And you know what I'm going to do? I'm just going to go up here, and instead of putting a 0.5 there, I'm going to delete the 0.5, and I'm going to insert 4, because 7 minus 3 is 4. So what's 2 plus 50 times the natural log of 4? It's 71.315. 71.315, which means that the shrub is now 71 millimeters above the ground. Right? That's what that means. Next it says, on what day after planting will the first signs of growth appear at the surface of the soil, and give a reason to justify what you did to determine your answer? Well, we want to know exactly when the first signs of growth are going to appear at the surface of the soil. So when does the answer go from being negative under the ground to being positive above the ground? Well, that's going to happen right when the shrub is at 0, right? So in other words, I'm going to set the height equal to 0. We want to be right at the surface of the soil. So I'm going to take 0, set it equal to the function 2 plus 50 natural log t minus 3. And then I'm going to solve for t to get the amount of time it'll take for us to get from negative to 0. Okay, so subtract 2 from both sides first, and we get negative 2 is equal to 50 natural log t minus 3. Dividing both sides by 50, I'll get t closer to being by itself, right? So we actually get negative 1 over 25 is what that fraction would reduce to, is equal to natural log of t minus 3. Right? And to get rid of the natural log, we need to take both sides and raise e to the power of both sides of the equation. So e to the negative 1 over 25 is equal to e to the natural log of t minus 3. And what will happen here is we're actually, again, that's how we undo the natural log part. So we're going to be left with t minus 3 is equal to e to the power of negative 1 over 25, right? So in other words, t is equal to e to the negative 1 over 25 plus 3. Okay, and what happens when we punch that into a calculator? Here's the punchline. E to the power of negative 1 over 25 plus 3 is equal to 3.96078. Which would round to 3.96. Well, we can't really see that very well. 3.961.